Good evening, and welcome. Tonight, as the stars begin their slow procession across the darkening sky, we turn our attention towards something extraordinary, not a distant signal from the depths of space, but rather a profound realization about ourselves, about the pale blue world we call home, and about the vast, indifferent cosmos that surrounds us. This is a story about discovery, a story about the moment when humanity first understood, truly understood, that we are not the center of everything, that Earth, our entire world with all its history and drama, is nothing more than a tiny speck suspended in an ocean of darkness so vast that the mind struggles to comprehend it. Because before we can understand where we might go, before we can dream of voyaging to distant stars or listening for whispers from alien civilizations, we must first confront a humbling truth. We are small, unimaginably, profoundly, cosmically small, and recognizing this smallness is not a moment of despair, but rather the first step toward genuine wisdom. Let us begin at the beginning, thousands of years ago. When humans first looked up at the night sky and tried to make sense of what they saw, the stars wheeled overhead in their eternal dance. The sun rose and set with perfect regularity, the moon waxed and waned through its phases. And at the center of it all, solid and unmoving, was Earth. Our Earth. It seemed obvious, intuitive, self-evident. Everything in the heavens revolved around us. The planets, whose name comes from the Greek word for wanderer, traced strange loops across the sky, but surely they too were circling our world. This was geocentrism, the belief that Earth occupied the central position in the cosmos. It was more than just an astronomical theory. It was a statement about human importance, about our special place in creation. We were not merely observers of the universe, we were its focal point, its reason for being. The ancient Greek astronomer Ptolemy refined this view into a sophisticated mathematical model that could predict the motions of the planet with remarkable accuracy. His system, developed in the 2nd century, would dominate human thinking for more than 1,000 years. But even in ancient times, there were those who dared to question this comfortable certainty. In the 3rd century before the Common Era, a Greek astronomer named Aristarchus of Samos proposed something radical, something that defied common sense and challenged humanity's self-image. He suggested that our Earth was not stationary at all, that it revolved around the sun, and that the apparent motion of the stars was caused by Earth's own rotation. It was a brilliant insight, a leap of imagination that anticipated the truth by nearly 2,000 years. But without telescopes, without precise measurements, without the mathematical tools to prove it convincingly, Aristarchus's heliocentric model remained little more than an interesting speculation, largely ignored by his contemporaries. The true revolution, the intellectual earthquake that would forever change humanity's understanding of its place in the cosmos, would not come until the Renaissance. In 1543, a Polish astronomer named Nicholas Copernicus published a book with a title that would become synonymous with radical change on the revolutions of the celestial spheres. In this work, Copernicus presented a detailed mathematical model in which the sun, not Earth, occupied the center of the known universe. The planets, including Earth, orbited around this central fire in circular paths. It was not a perfect system. Copernicus still clung to the ancient belief that celestial motions must be perfectly circular, which forced him to introduce complex corrections to match observations. But the core insight was revolutionary. Earth was demoted from its throne at the center of creation and reduced to just another planet, one among several circling an ordinary star. This was the Copernican Revolution, though the name is somewhat misleading because revolutions happened quickly, and this transformation took more than a century to complete. Copernicus himself was cautious, delaying publications of his work until the very end of his life, aware that his ideas would be controversial, perhaps even dangerous. Indeed, the response was slow. Many astronomers initially resisted the heliocentric model, not because they were foolish or stubborn, but because it contradicted both common sense and centuries of accumulated wisdom. If Earth was truly spinning on its axis and hurtling through space at tremendous speed, why did we not feel it? Why were we not flung off into the void? And if Earth moved around the sun, Why did the stars not shift their positions as we changed our viewpoint, showing the parallax effect that should accompany such motion? These were reasonable objections, and answering them would require decades of additional work. The next crucial step came from Johannes Kepler, a brilliant German mathematician and astronomer who worked in the early 1600s. Kepler inherited detailed observations of planetary motion from his mentor, the Danish astronomer Tycho Brahe, and he used these observations to refine the Copernican model. Kepler discovered that the planets do not move in perfect circles, as both Ptolemy and Copernicus had assumed, but rather in ellipses and elongated ovals with the sun at one focus. This discovery, along with his other laws of planetary motion, provided a much more accurate description of how the solar system actually works. The universe was revealing itself to be more complex, more mathematically beautiful than anyone had imagined. And then came Galileo Galilei, the Italian scientist who pointed his newly invented telescope at the heavens and saw things that no human had ever seen before. He observed mountains and craters on the moon, proving it was not a perfect sphere, as ancient philosophy had claimed. He discovered 4 moons orbiting Jupiter, demonstrating that not everything in the cosmos circled Earth. Most importantly, he observed the phases of Venus, the way the planet showed different amounts of illumination at different times, just like our moon. This observation was devastating to the geocentric model, because it could only be explained if Venus orbited the Sun, not Earth. The evidence was becoming overwhelming. Earth was not the center. We were in motion, spinning and orbiting, just another world among many. This intellectual shift, this slow erosion of geocentric certainty, was the first great trauma to humanity's cosmic self-image. It was not merely a technical correction to astronomical calculations. It was a philosophical wound, a fundamental challenge to our sense of importance and specialness. If Earth was not the center, then perhaps humans were not central either. Perhaps we were not the purpose of creation, but simply one outcome among countless others. A brief flicker of consciousness on an ordinary planet circling an ordinary star. The realization was both liberating and terrifying. Liberating because it freed us from old dogmas and opened the door to genuine scientific inquiry. Terrifying because it forced us to confront the possibility of our own cosmic insignificance. Yet this was only the beginning. As astronomy continued to advance, as telescopes grew larger and more powerful, as our understanding of the universe deepened, we discovered that even the sun itself was not the center of anything particularly special. The sun, that blazing furnace that gives us light and warmth and life, turned out to be merely one star among hundreds of billions in a vast spiral galaxy we call the Milky Way, and our sun does not even reside at the galaxy's center, but rather out in the suburbs, about 2/3 of the way from the core to the edge, in an unremarkable region between 2 spiral arms. The process of cosmic demotion continued. We were not at the center of the solar system. The solar system was not at the center of the galaxy. And as we would eventually discover, our galaxy was not at the center of the universe either. There was no center. The universe had no privileged location, no special vantage point from which to view creation. We were adrift in an endless sea of space and time, with no fixed reference point, no cosmic anchor. This long, slow erosion of geocentric identity represents a critical divergence in human understanding. We grasped our astronomical non-centrality mathematically centuries ago through the work of Copernicus and Kepler and Galileo and Newton, but there is a vast difference between understanding something intellectually through equations and diagrams and logical arguments, and experiencing it viscerally, emotionally, as a felt truth that penetrates to the core of your being. The transition from abstract theories to profound, shared understanding would require one more step. It would require that we leave Earth behind, that we travel out into the void and turn our gaze back toward home. Only then, only when we saw Earth not as an infinite plane stretching to the horizon in all directions, but as a finite sphere hanging against the blackness of space, only then did the full weight of our cosmic smallness become real, undeniable, impossible to ignore. The Copernican revolution taught us that Earth moves. But it would take the space age to show us what Earth actually looks like from the outside, to transform mathematical knowledge into emotional truth. And that revelation, that moment of seeing ourselves from a cosmic perspective, would change everything. It would birth a new way of thinking about our planet, about our responsibilities, about what it means to be human in an infinite universe. This is where our story truly begins, truly. And so we arrive at the inevitable question. Having understood our cosmic insignificance, having gazed upon Earth from the outside and recognized it as a fragile mote of dust suspended in a sunbeam, what lies beyond? If we dared to leave this pale blue dot, if we gathered our courage and ventured out into the vast darkness between the stars, what would we find? How far would we have to travel? And perhaps most importantly, what would such a journey do to us, to our bodies, to our minds, to the very essence of what it means to be human? The answer begins not with distant stars, but with the edges of our own solar system, that collection of planets and moons and asteroids and comets that orbit our sun. We imagine the solar system as a cozy neighborhood, a place we understand and have explored. We have sent robotic probes to every planet. We have landed on Mars, sampled the rings of Saturn, touched down on asteroids and comets. Surely the solar system is our backyard, a space we have mastered. But this comfortable assumption collapses the moment we examine the true scale of our cosmic neighborhood. When we think of the solar system, we usually picture the 8 planets, from Mercury closest to the Sun, out to Neptune. At the edge, Neptune orbits approximately 30 astronomical units from the Sun. An astronomical unit, abbreviated as AU, is simply the distance from Earth to the Sun, about 150 million kilometers or 93 million miles. 30 astronomical units sounds like a manageable distance, the sort of thing our spacecraft could reach within a reasonable time. And indeed, we have sent probes to Neptune. Voyager 2 flew past in 1989, capturing stunning images of that distant blue ice giant before continuing on into the darkness beyond. But here's where our intuition betrays us. The planets, those familiar worlds we learned about in school, mark only the beginning of the solar system, not its end. Beyond Neptune lies a vast, nearly empty expanse that dwarfs the planetary region. This is where the true solar system begins, a realm so enormous that the distances involved transform from spatial measurements into temporal ones. We are no longer talking about places we might visit, but rather about gulfs of time, so vast they exceed the entire span of recorded human history. The ultimate boundary of the solar system is marked by something called the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence. The Oort cloud is a vast spherical shell of icy bodies, billions upon billions of frozen comets, that surrounds the Sun at an unimaginable distance. These are the seeds of comets, pristine remnants from the formation of the solar system 4.5 billion years ago, preserved in the deep freeze of space. Occasionally, gravitational perturbations from passing stars nudge one of these icy bodies inward, sending it on a long plunge toward the Sun, where it blazes across our skies as a spectacular long-period comet before returning to the outer darkness. The Oort cloud begins at approximately 1,000 astronomical units from the Sun, and extends outward to perhaps 100,000 astronomical units. Let those numbers settle in your mind for a moment. 1,000 to 100,000 times the distance from Earth to the Sun. The nearest edge of the Oort cloud is more than 30 times farther than Neptune. The outer edge is more than 3,000 times more distant. This is the true extent of our Sun's gravitational dominion, the ultimate boundary where our star's influence fades and interstellar space truly begins. Now let us consider our ambassadors to this realm, the Voyager spacecraft, those twin robotic explorers launched in 1977 to study the outer planets. After completing their primary missions, both Voyager 1 and Voyager 2 continued outward, becoming the first human-made objects to leave the solar system. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind, that stream of charged particles flowing outward from the Sun, finally meets the interstellar medium and can push no farther. At approximately 120 astronomical units from the Sun, Voyager 1 entered interstellar space, the realm between stars. This achievement was celebrated as a historic milestone, and rightly so. Humanity had finally breached the wall, finally sent something beyond the protective bubble of the Sun's influence into the galaxy proper. But here's the sobering reality. Voyager 1, traveling at roughly 17 kilometers per second, one of the fastest objects ever built by human hands, has barely begun its journey to the true edge of the solar system. The spacecraft will take approximately 300 years just to reach the inner edge of the Oort cloud. And to fully transit the Oort cloud, to emerge on the far side, and truly leave the Sun's gravitational territory will require an estimated 30,000 years. 30,000 years? That is longer than the entire span of human civilization. Longer than agriculture, longer than writing, longer than cities and empires and everything we call history. This is the ultimate psychological and technological barrier, the true gate to the galaxy. The Oort cloud transforms interstellar space from a distance we might measure in kilometers into a measure of deep time, time so vast it renders human ambition almost meaningless. The void is not just empty, it is temporally empty, a desert of years that swallows generations whole. And yet, if we are serious about reaching other stars, about establishing humanity as an interstellar species, we must confront this barrier. We must find a way to cross not just the distances involved, but the time required. This necessity gives rise to one of the most ambitious and haunting concepts in all of space exploration, the generation ship. A generation ship, also called a starship ark or world ship, is a hypothetical spacecraft designed for voyages lasting hundreds or thousands of years. The premise is straightforward, perhaps deceptively so. Since we cannot travel faster than light, and since even reaching a significant fraction of light speed remains beyond our current technology, we must accept that interstellar journeys will take multiple human lifetimes. The original crew who depart Earth will never see the destination. They will live out their lives aboard the vessel, have children, grow old, and die, all within the metal corridors of the ship. Those children will do the same, and their children after them, generation after generation, until finally, centuries or millennia hence, their distant descendants arrive at the target star system. The concept is old, dating back to the early 20th century. In 1918, the rocket pioneer Robert Goddard sketched out ideas for interstellar arcs that could sustain crews for centuries. The Russian visionary Konstantin Tsiolkovsky expanded on these ideas in 1928, describing what he called a Noah's Ark for space, a vessel that would carry Earth's diversity to the stars. In 1964, NASA scientist Robert Enzmann proposed the most detailed generation ship design to date, a massive craft 600 meters long, powered by fusion reactors, carrying an initial crew of 200 with room for expansion. These were not idle fantasies, but serious engineering studies, attempts to grapple with the practical realities of interstellar travel. Modern analysis has refined the concept. A generation ship would need to be enormous, perhaps kilometers in length, containing everything necessary to sustain a complete miniature civilization. It would require closed-loop life support systems, biosphere gardens where plants could produce oxygen and food, water recycling so efficient that not a single drop is wasted, nuclear or fusion reactors to provide power for centuries. The ship would need to rotate to provide artificial gravity through centrifugal force, preventing the muscle atrophy and bone loss that plague astronauts in weightlessness. It would need radiation shielding to protect against cosmic rays, repair facilities to fix anything that breaks, and redundant backups for every critical system. And most importantly, it would need to be completely self-sufficient. There is no turning back, no resupply missions, no rescue if something goes wrong. Once the generation ship departs Earth, it is entirely alone, a tiny bubble of life and warmth drifting through an ocean of frozen vacuum. The crew cannot call for help. They cannot abandon ship. They either succeed in maintaining their artificial world for the entire duration of the voyage, or they perish in the darkness between stars. This isolation, this absolute dependence on the ship's systems and on each other transforms the generation ship from an engineering challenge into an existential crucible. Because the real challenges of a generation ship are not technical, but human. The question is not whether we can build such a vessel. Given enough resources and determination, we probably could. The question is whether human beings can survive the journey psychologically and socially intact. Can a community of hundreds or thousands of people live for generation after generation in a closed, artificial environment without descending into conflict, stagnation, or madness? Consider what life aboard such a ship would entail. You are born in a metal corridor. You grow up knowing only artificial light, recycled air, the same walls and faces you have seen every day of your existence. You have never felt wind, never smelled rain, never stood under an open sky. Earth is not a place you remember, but a myth passed down through stories, images on screens, records in a database. The destination star system is equally abstract, a goal you will never live to see. Your entire existence is the ship. The ship is your world, your universe, your reality. You are not traveling to somewhere. You are simply existing in transit, a state that will continue long after you die, and your children die, and their children after them. This represents perhaps the deepest irony of interstellar expansion. The generation ship, designed to carry humanity to the stars, might instead create an entirely new species, divorced from its origins, shaped by centuries of isolation into something we would barely recognize. The journey would not preserve human continuity across the galaxy. It would shatter it, creating isolated populations that diverge and evolve independently. The dream of interstellar colonization, of spreading humanity among the stars, might instead result in the end of a unified human identity, replaced by countless variations, each shaped by its own unique voyage through the dark. And so we confront the silent voyage, the deep dark that waits beyond our pale blue dot. The distances are not merely vast, they are temporally vast, measured in generations rather than years. The journey is not a trip, but a way of life, a state of existence that transforms everyone who undertakes it. The void between stars is not empty space to be crossed, but rather a crucible that reshapes body, mind, and culture, until the travelers no longer remember where they came from or why they departed. This is the price of reaching for the stars. Not death or danger, though those are certainly present, but rather transformation so profound that the humans who arrive are no longer the same species as those who departed. The silent voyage offers not triumph, but metamorphosis, not continuity, but evolution, not the stars, but exile among them. But perhaps the generation ship, for all its challenges and tragedies, represents a false hope, a dream born from the assumption that we control our own destiny in space. Because the truth, as we are beginning to understand, is far stranger and more humbling. Our journey through the cosmos is not determined by our technology, by our rockets and engines and clever engineering. It is dictated by forces so vast, so overwhelming, that human ambition becomes almost irrelevant in comparison. We are not the masters of our cosmic fate. We are passengers, carried along by invisible currents of gravity that flow through the universe on scales that dwarf galaxies themselves. Imagine standing on the deck of a sailing ship in the middle of a vast ocean. You can adjust your sails, steer your rudder, navigate by the stars. You feel like you are in control of your voyage. But beneath you, unseen and unfelt, ocean currents, thousands of kilometers wide, are carrying you along at speeds that make your efforts almost meaningless. You are moving not because of your own power, but because the entire ocean is moving, flowing in great circular patterns driven by temperature differences and the rotation of Earth itself. You can choose your direction locally, but your ultimate path is determined by forces far beyond your control. This is the situation humanity finds itself in on a cosmic scale. We live on Earth, which orbits the Sun, which orbits the center of the Milky Way galaxy, along with hundreds of billions of other stars. And the Milky Way itself, despite its almost unimaginable size, spanning 100,000 light years from edge to edge, is not stationary. It is moving. Accelerating, in fact, pulled by gravitational forces of such magnitude that they dominate the motions of thousands of galaxies across hundreds of millions of light years. This brings us to one of the most mysterious and profound discoveries in modern cosmology, the Great Attractor. The name sounds like something from science fiction, a cosmic antagonist, a malevolent force pulling everything toward its doom. The reality is both more prosaic and more awe-inspiring. The Great Attractor is not a single object, but rather a gravitational anomaly, a region of space containing an enormous concentration of mass that exerts a pull so powerful it is drawing our entire local group of galaxies, along with tens of thousands of others, inexorably toward it. The discovery of the Great Attractor began with observations of something called the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. If the universe were perfectly uniform, this background radiation should look exactly the same in every direction, but it does not. There is a subtle pattern, a dipole, a slight difference in temperature between one side of the sky and the other. This dipole tells us that our galaxy is moving through space at roughly 600 kilometers per second relative to the cosmic microwave background. That is more than 2 million kilometers per hour, fast enough to cross the distance from Earth to the Moon in less than 12 minutes. But moving toward what? Astronomers traced the direction of this motion and found that the Milky Way, along with approximately 100,000 other galaxies within a vast region known as the Laniakea supercluster, is being pulled toward a specific point in the sky. This point lays in the directions of the constellation Centaurus, hidden behind the plane of our own galaxy. The concentration of mass required to produce such a pull is staggering, estimated at 10 to the power of 16 solar masses. That is 10,000 trillion times the mass of our Sun, concentrated in a region roughly 300 million light-years across and centered approximately 147 million light-years away from Earth. This is the Great Attractor, and it represents a fundamental truth about the universe. Gravity is patient, inexorable, and utterly indifferent to human scales and concerns. On the timescales of galaxies measured in billions of years, gravity dictates all motion. We are falling toward the Great Attractor not because we chose to, not because any engine or force we control is pushing us there, but simply because mass warps space, and large concentrations of mass warp space profoundly. We are rolling down a gravitational slope that has been carved into the fabric of space-time itself. Yet here's where the mystery deepens. Despite decades of study, despite increasingly powerful telescopes and sophisticated observations, we still cannot see the Great Attractor clearly. The reason is both simple and frustrating. The Great Attractor lies directly behind the disk of the Milky Way, hidden in what astronomers call the zone of avoidance. Imagine trying to observe a distant object through a dense forest. The trees in the foreground block your view, scattering and absorbing the light before it can reach your eyes. The zone of avoidance is like that forest, except instead of trees we have stars, gas, and dust, the thick material that fills the planet of our own galaxy. When we try to look in the direction of the Great Attractor, our view is obscured by this intervening matter. Visible light is absorbed and scattered. Even longer wavelengths struggle to penetrate the cosmic fog. We can detect the gravitational pull of the Great Attractor. We can measure its effect on the motion of galaxies, but we cannot directly observe the source of that pull. This is cosmic irony at its finest. The very structure we call home, the Milky Way galaxy with its familiar stars and beautiful spiral arms, actively blinds us to one of the most significant gravitational features in our cosmic neighborhood. Our galaxy, the context that makes Earth possible, simultaneously prevents us from understanding our own motion through the universe. We are like sailors on a ship whose mass blocks their view of the compass, leaving them to navigate by indirect signs and partial glimpses. And yet, the story grows stranger still, because the Great Attractor, as powerful as it is not alone. Recent observations have revealed that the Great Attractor itself is being pulled toward an even larger concentration of mass, known as the Shapley Attractor, or Shapley concentration, located roughly 650 million light-years away. This structure contains dozens of galaxy clusters, representing an even more massive gravitational well. Our cosmic motion is not a simple journey toward a single destination, but rather a complex dance choreographed by multiple gravitational centers, each pulling on the others in an intricate pattern. But perhaps most fascinating of all is the counterpoint to these attractors, a phenomenon known as the dipole repeller. The name is misleading. The dipole repeller does not repel anything. Gravity, after all, is always attractive. There's no such thing as a negative gravity, no force that pushes objects apart. Instead, the dipole repeller is a vast region of space characterized by a profound absence of matter. It is a cosmic void, an underdense region containing far fewer galaxies than the average volume of space. Why does this matter? Because our motion through space is determined not just by what pulls us, but by what fails to pull us. Imagine two people pulling on opposite ends of a rope. If both pull with equal force, the rope does not move. But if one person pulls while the other lets go, the rope accelerates toward the person who is still pulling. The dipole repeller is like the person who let go. In the direction of the repeller, there is very little mass, and therefore very little gravitational attraction, opposing the pull of the Great Attractor and the Shapley concentration. The apparent repulsion is simply the absence of counteracting gravity. Our motion through the universe is thus shaped by both overwhelming presence and profound absence, by dense concentrations of galaxies pulling us forward and empty voids failing to hold us back. We accelerate not toward a single destination, but away from emptiness and toward density, following the gravitational gradient of the cosmic web. And here is where the ultimate irony reveals itself. Despite this inexorable acceleration, despite the fact that our entire supercluster of galaxies is being pulled toward the Great Attractor at hundreds of kilometers per second, we may never actually arrive. The reason is dark energy, that mysterious force that pervades all of space and drives the accelerating expansion of the universe. Dark energy acts like a kind of anti-gravity, though that description isn't perfect. It does not push on objects directly. Instead, it causes space itself to expand, stretching the fabric of the universe and increasing the distance between objects that are not gravitationally bound together. Locally, within our solar system or even within our galaxy, gravity is strong enough to overcome dark energy, keeping structures bound together. But on the scale of hundreds of millions of light years, dark energy dominates. The result is a cosmic race between gravity and expansion. The Great Attractor pulls us forward. Dark energy stretches the space between us and the attractor. And because dark energy is constant, filling all of space uniformly, while gravitational attraction weakens with distance, there comes a point where expansion wins. We are accelerating toward the Great Attractor. Yes, but the space between us and our destination is expanding faster than we can cross it. We are like runners on a treadmill that speeds up faster than we can run. No matter how hard we push, the finish line recedes. This is motion without a rival, acceleration without destination, an eternal journey toward a goal we will never reach. Our entire supercluster is caught in this gravitational trap, forever falling toward concentrations of mass that forever retreats beyond our grasp, and because the expansion of space is accelerating, driven by dark energy's relentless push, eventually even the light from the Great Attractor will be redshifted beyond detectability. Future civilizations, billions of years hence, will not even be able to see the object toward which they are being pulled. They will move through space for reasons they cannot observe, driven by forces they cannot measure toward destinations they will never comprehend. This is our cosmic context, the larger framework within which all human ambition must be understood. We speak of traveling to other stars, of building generation ships and sending our descendants across the galaxy. But we are already traveling. already in motion, already embarked on a journey far grander and stranger than any we could design. We are passengers on Earth, which rides the sun, which rides the Milky Way, which rides the cosmic currents toward invisible destinations at speeds that dwarf anything our technology might achieve. The unseen currents dictate our path. Gravity without consent, motion without control, destiny defined by concentrations of mass and voids of absence that operate on scales so vast they render human agency almost meaningless. We can choose to explore locally, to visit Mars or the moons of Jupiter, perhaps even to send generation ships to nearby stars. But our ultimate trajectory through the cosmos is not ours to determine. It was set in motion billions of years ago by the distribution of matter in the early universe. And it will continue billions of years into the future, long after humanity has either spread to the stars or vanished entirely. This is the humility that astronomy demands. Not just the recognition that we are small, though we are. Not just the acknowledgement that we are temporary, though we are. But the deeper understanding that we are carried, moved by forces beyond our comprehension or control, on a journey we did not choose toward the destination we will never reach. The generation ship is our dream of mastery. The great attractor is the reality of our subjugation. And between them lies the truth of human existence in an infinite, indifferent, magnificent universe. And so we find ourselves in a strange position. We understand our cosmic insignificance, the smallness of our pale blue dot against the vastness of space. We have contemplated the impossibility of the journey, the generation ships that transform travelers into something unrecognizable. We have traced the invisible currents that carry our entire galaxy through space toward destinations we cannot see and will never reach. All of this paints a picture of profound cosmic loneliness, of humanity isolated on a tiny world, drifting through an empty universe. But is the universe truly empty? Are we truly alone? This question, perhaps the most profound that humanity has ever asked, becomes urgent in light of everything we have discovered. Because if the universe is so vast, if there are billions of galaxies each containing billions of stars, if planets are as common as we now know them to be, then surely life must have arisen elsewhere. Surely intelligence must have emerged on other worlds. Surely there must be civilizations out there, civilizations far older and more advanced than our own, civilizations that have solved the problems of interstellar travel, that have spread across the galaxy, that have built empires among the stars. And yet we see nothing. We hear nothing. The galaxy is silent. Our telescopes reveal no megastructures, no signs of astroengineering, no vast networks of starships moving between systems. Our radio telescopes detect no deliberate signals, no messages beaming across the interstellar void. The search for extraterrestrial intelligence, decades of patient listening, has yielded only natural noise and a handful of intriguing but ultimately unexplained anomalies. The silence is deafening, the emptiness is profound, and this silence, this cosmic quietude in a universe that should be teeming with life, is known as the Fermi paradox. The paradox is named after physicist Enrico Fermi, who reportedly posed the question during a casual lunch conversation in 1950. The reasoning is simple and devastating. The Milky Way galaxy is approximately 13 billion years old. Earth formed only 4.5 billion years ago, meaning the galaxy had already existed for more than 8 billion years before our planet even came into being. If intelligent life is even moderately common, then countless civilizations should have arisen billions of years before humanity, even traveling at modest fractions of the speed of light, even pausing for centuries or millennia between each jump to establish colonies and build more ships. An expanding civilization could colonize the entire galaxy in just a few tens of millions of years. Tens of millions of years is nothing compared to the age of the galaxy. It is a geological eye blink, a brief moment in cosmic time. So where is everybody? If the galaxy is old enough for countless civilizations to have arisen, and if interstellar colonization is possible, even if difficult, then we should see evidence of these civilizations everywhere. We should be living in a crowded galaxy, thick with radio chatter and invisible engineering projects. Instead, we appear to be alone, the only intelligence in a vast and empty cosmos. This is the Fermi paradox, and it admits of no easy resolution. There are, of course, many proposed explanations. Perhaps intelligent life is extraordinarily rare, so rare that we are the only example in the entire galaxy. Perhaps intelligence arises often, but technological civilizations invariably destroy themselves before they can spread to the stars, victims of nuclear war or environmental collapse or some other existential catastrophe. Perhaps interstellar travel is simply too difficult and too expensive, too dangerous, and every civilization that considers it decides the cost outweighs the benefit. Perhaps advanced civilizations lose interest in expansion, turning inward to virtual realities or transcendent states we cannot imagine. Perhaps we are being deliberately avoided, placed in a kind of cosmic zoo or nature preserve, observed but not contacted by civilizations that prefer to watch without interfering. Each of these explanations has merit. Each can account for some aspect of the silence. But none of them feel entirely satisfying, because they all require us to believe that something prevents every single civilization from expanding, from broadcasting, from making its presence known. It seems implausible that every intelligence in the galaxy would make the same choice, follow the same path, encounter the same limitation, and yet the silence persists. This brings us to one of the darkest and most disturbing solutions ever proposed to the Fermi paradox. It is called the dark forest hypothesis, and it suggests that the galaxy is not empty at all. It is full of civilizations, countless intelligences watching and listening and hiding in the darkness. But they maintain absolute silence, not out of indifference or a technological limitation, but out of paranoid, ruthless, existential fear. The dark forest hypothesis is built on two simple assumptions. First, that survival is the primary, non-negotiable goal of every civilization. Every species, every intelligence, whatever its values or philosophy, must prioritize its own continued existence above all else. Second, that the total resources of the universe are finite. There's only so much energy, so much matter, so much space. As civilizations expand, they inevitably compete for these limited resources. Now add a third factor, uncertainty. When a civilization detects another civilization, it faces an impossible dilemma. It cannot know the other civilization's true intentions. It cannot know whether the other is peaceful or aggressive, whether it will be satisfied with its current territory or whether it will continue expanding, eventually coming into conflict. It cannot know how rapidly the other civilization is developing, whether it will remain at its current level of technology, or whether it will advance to the point where it becomes an existential threat. And most critically, it cannot know whether the other civilization is making the same calculations, whether it too is considering a preemptive strike. This is the essence of the dark forest. The universe becomes a game of mutual paranoia, where the safest strategy is to remain hidden and to eliminate any other civilization you detect before it can eliminate you. It does not matter whether the other civilization is actually hostile. It does not matter whether they would prefer peaceful coexistence. The mere possibility of future conflict, combined with the inability to verify intentions and the premium placed on survival, makes preemptive destruction the rational choice. The name Dark Forest comes from a vivid metaphor. Imagine the galaxy as a dark forest at night. You're a hunter moving through the trees, armed and alert. You know that other hunters are also in the forest, but you cannot see them. You cannot know their positions, their intentions, their capabilities. Every sound, every movement could be a threat. The forest is silent because every hunter knows that making noise reveals their position, and revealing your position invites attack. The only safe strategy is to move quietly, to listen carefully, and to shoot first at anything that makes a sound. In this framework, the Fermi paradox is solved. The galaxy is not empty. It is full of civilizations, perhaps hundreds or thousands of them, all maintaining strict radio silence, all carefully hiding their presence, all watching the darkness for signs of others, all ready to strike instantly and ruthlessly at any civilization foolish enough to reveal itself. The silence we hear is not absence, but strategy. It is the sound of countless civilizations holding their breath, waiting, watching, preparing to destroy anything that moves. And this brings us to a deeply uncomfortable realization: humanity has not been silent. For more than a century since the invention of radio and television, we've been broadcasting our presence to the cosmos. Every radio transmission, every television signal, every radar pulse is radiated outward into space at the speed of light, creating an expanding bubble of electromagnetic noise centered on Earth. This bubble now extends more than 100 light years in all directions, encompassing hundreds of star systems. We have announced ourselves to the galaxy. We have lit a torch in the dark forest. This is correct. This is not an act of hopeful curiosity, but one of suicidal recklessness. We have revealed our position, our level of technology, our existence to any civilization within that 100 light-year radius. And if those civilizations are following the dark forest logic, if they calculate that any revealed civilization is a potential future threat, then our broadcast may have already triggered a response. Somewhere in the darkness, an attack may already be in motion. Relativistic projectiles or self-replicating weapons or something we cannot even imagine, racing toward Earth at a significant fraction of light speed. We would not see them coming. We would have no warning. We would simply cease to exist, vaporized in an instant by a civilization that destroyed us not out of hatred but out of cold. This scenario is speculative, of course. It requires assumptions about alien psychology and game theory that may not hold. But it illustrates a critical point. In the absence of communication, in the absence of trust, cooperation becomes impossible, and paranoia becomes rational. The very isolation that makes space travel difficult also makes interstellar relations almost impossible. We cannot negotiate with civilizations, we cannot detect, we cannot build trust with species whose thoughts and values are entirely alien. And in that vacuum of understanding, fear fills the void. The dark forest hypothesis suggests that advanced technological capability must be decoupled from visibility. The most successful civilizations, the ones that survive and thrive over billions of years, are those that master total concealment. They do not broadcast, they do not build obvious megastructures, they minimize their electromagnetic emissions. They hide in plain sight, indistinguishable from natural phenomena, waiting and watching while younger, less cautious civilizations announce themselves and are eliminated. If this is true, then humanity's desire to communicate, to reach out, to announce our presence through projects like the search for extraterrestrial intelligence and deliberate interstellar messages may be our defining vulnerability. The qualities we value most, curiosity, openness, the desire for connection, may be precisely the traits that mark us as naive and dangerous in the eyes of more experienced intelligences. Our broadcasts are not greetings but threats, signals that we have reached a technological level where we could potentially become a future competitor for resources. The paradox deepens. If we maintain silence, if we follow the dark forest logic and hide, we condemn ourselves to eternal isolation. We will never make contact with other civilizations, never benefit from their knowledge, never participate in a galactic community. But if we broadcast, if we announce our presence, we risk destruction by civilizations following the same paranoid calculus. There may be no solution, no strategy that guarantees both survival and connection. We may be forced to choose between loneliness and extinction. And so the silent hunters remain hidden, if they exist at all. The galaxy may be teeming with life, with intelligence, with civilizations watching each other across the light years through careful paranoid observation, each one holding its fire only because it has not yet detected a clear enough target. Or the galaxy may be truly empty, and we are alone, shouting into a void that will never answer because there is no one out there to hear. Both possibilities are terrifying in their own way, but they share a common theme with everything we have discussed. Whether we are alone or surrounded by hidden hunters, whether we face the emptiness of a dead universe or the paranoia of a crowded one, the conclusion is the same. We are isolated, not just physically, separated by distances that take generations to cross, not just gravitationally, carried by currents we cannot control toward destinations we will never reach, but existentially. The universe does not care about us. It does not protect us. It offers no guarantees of contact, of friendship, of meaning. We are on our own, a brief flicker of consciousness on a tiny world, surrounded by either emptiness or threat, facing a future that is both unimaginably vast and profoundly uncertain. The more we understand about the universe, the more isolated we realize we are. The cosmos that should be filled with voices is silent, and we are left to wonder whether that silence is the peace of an empty universe, or the held breath of countless civilizations waiting, watching, preparing to strike at anything that dares to break the quiet. Either way, we are alone with our questions, our fears, and our tiny torch burning in the infinite dark. And now we come to the end, though it is not truly an end, but rather a glimpse of endings yet to come. We have journeyed from Earth's demotion from the center of creation to its revelation as a pale blue dot. We have contemplated the impossible distances that separate us from other stars, and the generation ships that would transform travelers into strangers. We have traced the invisible gravitational currents that carry our galaxy through space toward destinations we will never reach. We have confronted the possibility that we are either alone in a dead universe or surrounded by silent hunters waiting in the dark. All of this paints a picture of isolation, of humanity adrift in an indifferent cosmos. But even this isolation, as profound as it seems, is temporary because the universe itself is evolving, changing in ways that will eventually render even our current understanding obsolete. The final act of the cosmic drama is not about human ambition or alien civilizations. It is about the fate of everything, the ultimate destiny of space and time and matter itself. To understand where the universe is going, we must first understand where it came from. Approximately 13.8 billion years ago, the universe began in an event we call the Big Bang. This was not an explosion in space, but rather an explosion of space itself. The sudden appearance of all dimensions, all matter, all energy, condensed into a volume smaller than an atom. In the first fraction of a second, the universe underwent a period of exponential expansion, called cosmic inflation, growing from quantum scale to cosmic scale faster than the speed of light. This was possible because space itself was expanding, and space is not limited by the speed of light. Only matter and energy within space are constrained by that universal speed limit. After inflation ended, the universe continued to expand, but at a much slower rate. The tremendous energy of the Big Bang began to cool and condense into particles. Within the first second, quarks combined to form protons and neutrons. Within the first 3 minutes, these nuclear particles fused together in a process called Big Bang nucleosynthesis, creating the first atomic nuclei, mostly hydrogen and helium with traces of lithium. For the next 380,000 years, the universe remained too hot for these nuclei to capture electrons and form complete atoms. It was an opaque plasma, light scattered endlessly by free electrons, unable to travel in straight lines. But as the universe continued to expand and cool, a critical threshold was reached. Electrons slowed down enough to be captured by atomic nuclei, forming the first neutral atoms in an event called recombination. Suddenly, light could travel freely through space without being scattered. The universe became transparent. This moment, roughly 380,000 years after the Big Bang, released a flood of light that has been traveling through space ever since. We can still detect that light today, stretched by cosmic expansion into microwave wavelengths, forming what we call the cosmic microwave background radiation, the oldest light in the universe. A baby picture of the cosmos, taken when it was less than 1% of its current age. Over billions of years, gravity continued to shape the cosmos. Stars collected into galaxies. Galaxies gathered into clusters. Clusters organized into vast filaments and walls, separated by enormous voids, forming what astronomers call the cosmic web, the large-scale structure of the universe. This is the universe we inhabit today, roughly 13.8 billion years after its fiery beginning, a vast expanse of space containing hundreds of billions of galaxies, each with hundreds of billions of stars, all slowly evolving, moving, changing under the patient, relentless influence of gravity. This is the enduring value of consciousness, the only force in the universe that temporarily resists the trend toward entropy and meaninglessness. We are the universe's way of understanding itself, brief flickering flames of awareness in the cosmic night, precious precisely because we are temporary. The mote of dust, for all its physical insignificance, contains something the rest of the universe lacks: the capacity to perceive, to reflect, to generate meaning from the raw material of existence. We are the dream of dust, and that dream, however brief, is the only thing standing between the cosmos and complete empty silence. And so we tell our story, we record what we have learned, we preserve the knowledge that future civilizations may lose. Not because it will save us, nothing will save us. The universe is indifferent and the ending is written. But because in the act of understanding, in the moment of seeing ourselves clearly against the infinite dark, we achieve something rare and precious. We become, for just an instant, truly awake.